Everyone, welcome to today's activity. Today we will be doing activity number 15, the very first activity of chapter 20, carboxylic acid. So in this chapter, in the very first part, we will touch based on some of the past concepts that you have probably learned in Chem 80, such as boiling point, acidity, and some reactions that help prepare carboxylic acid. Firstly, let's look at number 1. And for number 1, the first thing I like to do is looking at functional group, because when looking at functional group, we can tell which kind of intermolecular force is happening within the structure. Firstly, let's highlight all the functional group that we can see. So let's start from the very end. See carboxylic acid, ether, alcohol, and D is not actually a functional group. Let's start with the very first three. So one thing they all have in common is that they're just carbon chain, with A having one substituent. It actually create a little gap in between structure when you stack them all together. So we can decide that it has a lower boiling point when compared to B, but a higher boiling point when compared to C, because C is much bulkier. So now let's consider D and F, because it doesn't really have hydrogen bonding within the structure, but it has dipole-dipole force. So what we had to do is looking at the dipole. So what we have to look for is the difference in electronegativity of bonded atom. So when we look at the electronegativity chart, we can make the conclusion that electronegativity between C and Cl would be 0.61, while for oxygen is 0.89. And therefore, we can conclude that F actually has a lower boiling point than D. When comparing between E and G, we can both see that it has OH in there, so that would be your hydrogen bonding. However, G has a carbonyl group, so that slightly increased the boiling point. So G would actually have a higher boiling point than E. So this should be your answer. Let's start with number 2. So when considering the order of increasing acidity, we first has to consider the factor that affect the stability of the negative charge. And one way of doing this is to follow the Ariel rule. So firstly, let's circle the hydrogen that would lead to give rise to the negative charge. So for B, there are actually two H that could be possible. However, we can just consider one. C. So firstly, when we look into the structure, we can see that A, C, D, E all have oxygen having negative charge after the hydrogen leave. So we can conclude that they will all be more stable than B. B would be the least. Moving on to D and E, we can see that D and E both have fluoride, and fluoride, being a very electronegative atom, can actually pull electron density towards them, therefore stabilizing the negative charge. And this fall into the I portion, induction of Ariel. So we can conclude that D and E would be more stable than the other. However, because E has more fluoride, so E would be the most stable between the two. Now let's look at A and C. We can see that negative charge on oxygen. However, because C has a carbonyl group right next to the OH group, so we can conclude that the resonance for C would be better, so C would have a higher acidity when compared to A. So this should be your answer. And where phenol would go into that ranking should be right in between A and C. This is due to the fact that phenol has one oxygen atom, and there is resonance happening within the structure. However, resonance between carbon atom is not as good spreading charge as oxygen atom. Okay, now let's move on to number 3. So in number 3, we're actually looking back at different reaction that we have to make carboxylic acid. So firstly, let's look at oxidative cleavage of alkyne. So what happened in this reaction is actually oxidative cleavage will break the triple bond, giving rise to two different carboxylic acid. So in this case, it will produce two different structure. And for the second one, same reaction, it will give a rise to two identical structure. Secondly, let's look at oxidation of primary alcohol. So strong oxidizing agent can be used to oxidize primary alcohol to produce carboxylic acid. So in this case, this would be the structure. However, when using a secondary alcohol, we are not able to make carboxylic acid. Instead, it will be oxidized to a ketone. The next one we're going to do is oxidative alkyl benzene. So what happened in this reaction is an any alkyne group on an aromatic ring will be completely oxidized to give benzoic acid, provided that the benzylic position has at least one hydrogen atom. Right in this position, there is no an atom attaching to this carbon, so this position will not give rise to a carboxylic acid functional group. However, when we look down here in this carbon, due to the fact that there are one hydrogen atom, we can make a carboxylic acid in that very position. So now that we have covered all the old reaction, let's move on to the newer reaction that we will be learning today. So there's actually two methods of making carboxylic acid that we're going to learn, which one being the nitride hydrolysis and one being Grignard reagent with carbon dioxide. As you can see from these two reactions, you can see that we require a starting material with bromide already attached to it. And what's going to happen here is in this bromide position will give rise to the carbon position of the carbonyl group. So you're essentially adding one more carbon into the parent chain. So the product of these two reactions should look very similar. Let's try some synthetic strategy for the following targets below. Let's work backward from the product. So we know that we need to attach a carboxylic acid right in this position. So we could try to attach a Br group right here. The very first thing we have to do is using the NBS reaction. And this actually caused the Br to attach right in the middle. Next, we can use elimination to create a double bond. And then we can use HBr to give rise to a Br group right in this position. And then from here on, we can use either one of these two reactions to give rise to our ending product. So the next one, very similar. However, right now, the carboxylic acid would be right in this position. So we can conclude that we need to add the Br group right here in order to give rise to such product. So very similarly, let's use NBS. Your bromine group should be attached right in that position because benzylic position. And from this point on, it's much more easy. You can use both reactions that we have discussed earlier. And this should give you okay, let's move on to the second one. So this one is actually a little bit trickier because if we want to add Br right into this position, we have to consider the fact that there's an OH group right in this position and we need to protect it first. So let's start with protecting your alcohol group. And then from now on, we can use the same method, NBS, to add our Br group. And then use any of the two reactions that we have covered earlier. And this should give you structure. And from here, we can actually deprotect the alcohol group to give rise to the final product with TBAF. Moving on. So as you can see, we have to provide a mechanism for the following reaction. When looking at our starting material, we can see that it's a Grignard reagent. And due to the fact that it's a Grignard reagent, it will have a very negative carbon. And this is how your structure should look like. And due to how negative it is, it will actually perform a nucleophilic attack towards the positive carbon in CO2 and give rise to a carboxylate ion. And this carboxylate ion, in the presence of acid, will actually protonate to give rise to our final product. So that's all the steps that we need to do for number 5. Now let's move on to number 6. So in number 6, we actually have to provide a mechanism of nitride hydrolysis to carboxylic acid by filling in all these curved arrows. So this reaction actually starts with a proton transfer step where the nitrogen group will take away one hydrogen from the acid, and this will create an activated nitride group. In this next step of nucleophilic attack, your water will act as a nucleophile to try to break the pi bond. And nitrogen will actually pull all those electrons towards itself. In the very next step, proton transfer, this water now will act as a base to take away your hydrogen to give rise to this structure right here. And our goal right now is to remove the nitrogen by making the nitrogen a good leaving group. So we can add H one more time to give the overall structure a positive formal charge. And that will give rise to two structure right here. So what's going to happen is it will try to rearrange itself, making the double bond of the nitrogen group become a single bond. Proton transfer will occur one more time to give you this structure. And we will actually stop here because the last part will be explored at the very end of my chapter. So let's move on to question number 7. We can fill in the empty box with the proper reagent. To go from the very first structure to a second structure, we can just use what we have been using so far, NBS, to attach the bromine group. And then to give rise to this carboxylic acid, we can use one of the two reactions that we have just learned. Then, if you can compare this structure, the third structure, and the fourth structure, we can see that the carboxylic acid group become just an alcohol group. So we can use reduction agent. In this case, let's use LAH because NaBH4 is not strong enough to reduce carboxylic acid. And water as a proton source. And from the fourth structure to the fifth structure, we can see that the alcohol group become an aldehyde group. And one reaction that gives rise to that would be using PCC. And then we can use a Grignard reagent to get final product. And we have to add water afterwards. Okay. Now let's move on to number 8. Below is the 10-methanolysis of the following acid halide that give rise to two different structures, a methyl ester and an unknown compound with a molecular ion of 152.2. Our job is to determine the structure of the unknown compound. So firstly, let's look at the proton MMR. Look at the 4 ppm position where there is a peak that indicates that we have a methoxy. Nextly, at 7 and 8 ppm, there's our two peaks pretty close together, and this is actually indicating that we have an aromatic in our unknown structure. And lastly, there is an age group very upfield between 12 and 11 ppm, and the only option for that would be carboxylic acid. Moving on to the carbon MMR, we can see that there's our two peak at 172 and 167. That could be a good indicator. Carbonyl group, and this region right here with 3 different peaks would be an indicator that we have an aromatic in our structure. And lastly, in 64 position, we have a methoxyl group indicator. And based on our carbon and proton NMR, we can conclude that our structure has an aromatic compound within it, also a carboxylic acid, and an ether group. So that should be your final compound. Now, moving on to number 9, our job here is to provide the IUPAC name along with drawings based on the IUPAC name for the following question. So first, let's start with A. So in A, we can see that we have 2 carboxylic acid functional group and a carbon chain 5 carbon long. So let's start drawing 5 carbons. 1, 2, 3, 4, 5. The carboxylic acid will locate at both ends of the parent chain. Okay, moving on to B. Now let's highlight each part of the structure. So first we have this portion of the structure that indicate that this is benzoamide. And next we have a methyl group that attached to the nitrogen atom. So we could write it as N-methyl to indicate that this methyl is attached to the nitrogen. Moving on to C, let's start with highlighting our parent chain. So remember, for such structure, the parent chain should be the longest chain that include our functional group, which is the carboxylic acid. Now let's count how many carbon is in the chain. So let's start right here with 1 being the position of the carbon in the carbonyl group. 2, 3, 4, 5, 6. So we know our parent chain is going to be a hexanoic acid, and at the second position we have a substituent. So it's going to be 2-ethyl hexanoic acid. Okay. Now moving on, D, we can see that we have an acid anhydride, and how we would name that is stating our substituent. So first we have acidic isopropanoic and that should be the name for our compound D. Moving on to E, looking at this structure, we can see that there are 1 carboxylic acid functional group, and this will attach to a 6 carbon 2, 3, 4, 5, 6. And keep in mind there will be an extra carbon of the carboxylic acid, so that would make the chain 7 carbon long. Okay, moving on to F. Let's first start out by highlighting our functional group, which in this case is amide. And as you can see, nitrogen is connected to 2 phenyl group. So how we would reflect that in the name, we should put N-N-diphenyl acetamide. Now moving on to G, we can see that we have an ester as our functional group. So how we would name this is phenyl propanoate. Lastly, for H, let's start out by numbering our parent chain. Start with the carbon in the carbonyl group. So the name for this compound would be butanoid bromide. Okay, so that concludes today's activity. So in today's activity, the very first part of our activity today, we touch base on some familiar concept that we have learned about in Chem 80, which include boiling point, acidity, and also past reaction that we use to prepare carboxylic acid. In the latter part, we learn new method, new reaction to create carboxylic acid, along with learning how to name carboxylic acid and their derivative. I hope you guys enjoy and find this video helpful. Thank you so much for watching.